What is up, AS Math? It is Mr. Knight back again, giving you this time a double-decker action. We are going to be looking at acceleration and these things called Suvat equations. It's just an acronym for a bunch of equations that you're going to need in order to be successful in this class. So, question for you guys. If velocity is the change in displacement over time, what do you think the change in velocity over time is? I want you to take a second and talk to a partner, and we'll see what we come up with. And go. All right, we're back. Let's answer that question. So, if you couldn't tell by the title of this, or for those of you who have actually taken physics classes before, you know I am talking about acceleration. Okay, acceleration is that change in velocity over time, and it just measures how quickly the velocity is changing. That is a quick, rough definition of what acceleration is. You can accelerate, you can decelerate. Either way, you are accelerating. And notice I'm saying accelerate and decelerate. We'll talk about kind of what the differences are in a little bit here, okay? So, for an object moving at constant acceleration, again, do not write this black part down. I'd rather you write the blue part down. Acceleration is equal to the change in velocity divided by the time taken. So, our change in velocity would be our final velocity minus our initial velocity, which we call v and u. And that is divided by the time taken, which is t, and a is our acceleration. So we're going to be working with this equation just a little bit for some of these initial problems, and then we'll get into the Suvat equations and look at those. Okay? So let's actually see what accelerate and decelerate means, and kind of how direction works with this, because acceleration is a vector. It has a direction, but it doesn't work exactly the same way as displacement and velocity, right? So if I was moving in the positive direction, then my displacement's positive, and my velocity will be positive as a result. Here, though, I can have a velocity that is positive, but I can also have a negative acceleration. That's kind of weird, but let's think about that for a second. If I'm driving in my car and I'm going 30 miles per hour and I start hitting the brakes to decelerate, well, I'm not instantly going negative, velocity or anything. I'm not at a negative speed, even though speed can't be negative. I'm not negative for that. I'm just slowing down. So my velocity is still positive, but my acceleration is negative, which is causing it to decelerate. So let's look at two cases. By the way, Camber and those of you who made fun of my drawings, I came back this time with some cars, which you're probably going to make fun of right now, okay? Don't hate, appreciate, okay? They're quick to make. So let's look at this first case right here. An increase in velocity is simply a positive acceleration. So it really just comes down to, is your velocity increasing? So is your final velocity greater than your initial velocity, which you can see here? So we're still going the positive direction. But I'm going from 20 meters per second to 30 meters per second. So I'm having a positive acceleration. I have to accelerate to go faster. Likewise, even though I'm going in the positive direction, a decrease in my velocity equals a negative acceleration. So if I'm starting at 20 meters per second for my initial, but my final ends up being less than that, so 10 meters per second, well then I am decelerating. I have a negative acceleration in order to slow down. Okay, that is how your braking is working, and that's how that change in your velocity is being affected by, well, the acceleration, right? So go ahead. You don't need to draw these cars or anything, but I want you to kind of get this idea, right? An increase in velocity is a positive acceleration. A decrease in velocity is negative acceleration. And let's move forward with that, okay? There is another equation we can use that we are definitely going to write down and get, and it's this guy right here. It's an alternative form for displacement, and it was just taken from this average velocity equals displacement over total time. If a is constant, and really for all these equations we are assuming that acceleration is constant, we can use the formula for displacement, right? This is equal to 1/2 times u plus v times t. So it's really the average of our velocity, right? So the initial plus the final divided by 2 times the time. So it's literally just our velocity times our time, so if I move the time over in here, velocity times time does equal displacement. And that's what's going on here. This is literally the average velocity part right here, and then this t part is that time. So all these equations are very related to each other, so we might need to use that guy alongside with our acceleration equation that we just got. So let's take an example problem. Let's see how to use acceleration. So a parachutist falls from rest to 49 meters per second over 5 seconds. We need to find the acceleration, okay? Well, when we say from rest, that just means that your velocity is 0, okay? If you're not moving, so I'm not moving right now, I don't have a speed. It is 0, right? So that's what that means when you hear at rest. It's kind of like a hot word that you're looking for. And so we can use this acceleration equation, the one that we just got, right? I know that my final velocity is, well, going to be 49 meters per second. And from rest, the initial velocity would be 0. So from rest to 49, and it took 5 seconds. So if I plug all that stuff in, I end up getting a very common number that we will run into later on, which is 9.8. 9.8 what? Huh. Yeah, we should probably talk about that, huh? What are the units of acceleration? Well, I decided to go ahead and do this for us. I plugged into my equation A equals, on top would be in meters per second, divided by seconds. So if I do meters per second divided by seconds, I do keep change flip when I'm dividing fractions. I get meters on top, and I get seconds times seconds, so that's seconds squared. So it's actually 9.8 meters per second squared. And this is how the book likes to write it. Okay? Meters per second squared. And that 9.8, if you're looking at that, I wonder if you guys know what that is. Let me know what that is. Go. All right. This is just the gravitational constant. This is the acceleration due to gravity on Earth. It is mostly constant everywhere we go, depending on where you're at. Okay. So 9.8 meters per second squared. We will see that again later on. Let's see another equation. Let's see another example. For this guy, we have a tractor, and it's accelerating from 5 meters per second to 9 meters per second at 0.5 meters per second squared. We need to find the distance covered by the tractor in that time. Well, we need to find the distance. So I want to use that displacement equation, S equals 1/2 U plus B times T. Well, let's write down what we know. We know our initial velocity. Well, we started from 5 meters per second. I know my final velocity. It's 9 meters per second. And I know my acceleration. Well, that is 0.5 meters per second squared. Well, this doesn't ask for acceleration, but it asks for time, and time is crap. We don't have the time. Okay? That's a little unfortunate. We don't have the time. We can solve for the time, though. Maybe we don't want to use this equation just yet. Maybe we want to pump the brakes. Okay, so we don't know what that is yet. Is there a way we can solve for it? Of course there is. Okay, this is math after all. All right. So we know that other equation, A equals V minus U divided by T. We know we could solve for T using that equation. We have an A, V, and U. So let's rearrange this equation as if we were solving for T. Well, if I multiply T to both sides, right, I would get AT equals V minus U. And then finally, I need to divide both sides by A in order to get T by itself. So T equals V minus U over A. And now let's actually plug some stuff in. T equals, well, we have 9 minus 5 on top, so that's 4 over 0.5. And when we do that, we get 8 seconds for T. Now we actually know what that is. So now let's actually figure out the distance covered by this tractor, because that is the most pressing issue, is finding how far tractors travel, okay? So S equals 1/2, and then we have our 5 plus 9, which is 14 in there, and then times our 8. So basically 1/2 of 14 is 7 times 8, so our distance traveled was 56 meters. Alright. Nice, we're becoming farmers in real time using math. That is kind of what I've been trying to get you guys to do from the get-go, is become farmers. That's all. Agriculture. Yes, we need more agriculture. Now, let's get into some more interesting equations, because there's a reason I combined this exercise and exercise 1C, because they're really the same thing. It just goes a little bit deeper. So we have a bunch of equations for constant acceleration. These are called the Suvat equations. And this is them right here, okay? There's 5 of them right here. These 5 equations are probably some of the most important equations that we're going to do in mechanics, especially with acceleration. So we really are going to get a lot of practice with them. So for objects traveling, and you don't need to write this part out, just write your equations down. For objects traveling at constant acceleration for a time t with initial velocity u, final velocity v, and the change of displacement s, we have these 5 equations. They all really are equations that come from one another. So for example, I could take this guy and derive some of these other equations. I'm not worried about deriving. I'm more concerned with, can we use these equations? All right? So we'll go ahead, we'll pause the video if you have to write these down, but as I record, I'm going to move on to the next part of this, which is this first example problem, which is a doozy, okay? So, caveman write it. Don't try to write all of it. Get the key ideas down, okay? So, a go-kart travels down a slope of length 70 meters. It is given a push and starts moving with initial velocity of 3 meters per second and accelerates at a constant rate of 2 meters per second squared. Find its velocity at the bottom of the slope. And then part B says find time taken to get to the bottom. So how long did it take for it to travel to the bottom? Now, when we're doing these problems, there's really 2 steps to helping you solve it. First thing is first. You can list the variables, or draw a picture, or do both. Whichever you think is going to be most appropriate for this problem. Honestly, if you want to do both, you can. For the purposes of this problem, I'm just going to list the variables, okay? I'm going to list what we know. Well, we know some of this stuff, right? There's also stuff we don't know. We don't know the time. That's what we have to find for part B. I don't know the final velocity, right? That's the velocity at the bottom of the slope. Don't know what that is yet. We got to find it. But I do know what my displacement, my initial velocity, and my acceleration are. This is 70 meters, right? Down a slope of 70 meters. We had an initial velocity of 3 meters per second, and it accelerated at 2 meters per second squared. So now it comes down to, well, what equation are we going to use of those 5 Suvat equations? This is what you do. You're going to pick the equation with known variables and the one you want to solve. So for this first part, we want to find v, and we know s, u, and a. We don't know t. So if we can pick an equation that does not have t in it, that's probably our best bet. If you're looking at this, maybe you determine it would be this guy right here. And you'd be right. V squared equals u squared plus 2as. We can plug a bunch of stuff in and solve for v. So let's actually do that. Well, our v squared equals our 3 squared plus 2 times our 2 times 70. And now let's work that guy out. V squared equals 9 plus, we got 4 times 70, that's 280. And so we have v squared equals 289. And if you take the square root of both sides, plus or minus, we're going to end up with v equals plus or minus 14. Plus or minus 14 meters per second. Now, we have 2 answers. That doesn't really make sense. But let's think about this for a second, okay? So now this is where context really comes in handy. It's given a push, it starts moving with initial velocity, and it's going down a slope. Is it going to end up slowing down or going the other direction, the negative direction? No, it's not. It's going to speed up to 14 meters per second. So we don't need the negative We only need the positive 14 meters per second. Sweet. Now part B is saying, find the time taken to get to the bottom. Well, now we know what our V is. And we need to solve for t. Now, if you're looking at your equations, there are a lot of equations that have t in it. Okay? So what we got to do is we just need to pick the one that we think is going to be the easiest at this point. If it's my money, it's going with this first guy right here. We now know the final velocity. So let's do 14. This is part B now. 14 equals our u, which was still our 3, plus a, which is 2, times t, which we don't know. Okay? So let's subtract 3 over. Get 11 equals 2t. And if you divide both sides by 2, t is going to be 11 halves, which is 5.5 seconds. Okay? So, again, if you follow the step-by-step 1 and step 2, like list the variables, draw a picture, and then pick the equation with known variables and the one you're solving, these problems aren't too bad. They can be tricky, okay? So really, pay attention to what you're reading. And these are like the ultimate word problems, man. If you've struggled with word problems your whole life, you're going to get good at them in a hurry or die trying. You won't die, but you might end up trying, which is all I could ask for, okay? Let's do one more example, and then we'll end things, okay? Example, we have a golf ball being struck 10 meters from a hole, and it's rolling towards the hole. It has an initial velocity of 2.4 meters per second when struck, and it decelerates at a constant rate of 0.3 meters per second squared. Does the ball reach the hole? Now, let's write down some of the known variables that we have and see what we can come up with, okay? So again, 10 meters from the hole, that might be important. It has an initial velocity of 2.4 meters per second. Okay, u equals 2.4 meters per second. And it decelerates at a rate of 0.3 meters per second squared. Because it decelerates, that means the acceleration's negative. It's slowing down. Okay? Does the ball reach the hole? So as I read that, the meaning of does the ball reach the hole is a fancy way of asking what is its distance traveled. Because if it travels 10 meters, then it's probably reached the hole, right? But if it doesn't travel 10 meters, then it's not going to reach the hole. So we actually don't know what the displacement is of the ball, because that's what we're looking for. We also don't know the time, right? We don't know the time at all that this ball's been rolling. We kind of know the initial, or we know the final velocity. Eventually it's got to stop rolling, so that's useful. Just write it down for right now, see what we know. Well, let's look at our Subat equations and let's see what we can come up with, okay? Well, I do think, because we need to find the displacement of this ball to see if it's 10 meters, we're going to have to use a displacement equation. We're going to have to use one of these three guys. Unfortunately, they all incorporate t. They do. So, what we can do is, we can solve for t first, and then we can go ahead and try to find displacement. Well, if I'm looking at this, and I'm trying to solve for t, this first equation might be our best bet. We have a, we have u, and we have v. So let's plug some stuff in and solve for t. Kind of rhymed a little bit. Let's see what we got. So v equals u plus at. Let's plug in what we know. We know v is 0, u is 2.4, a is negative 0.3, and t is t. So let's subtract 2.4. And once we go ahead and we divide both sides by negative 0.3, we actually get 8 equals t. So about 8 seconds. Sweet. Let's hold on to that guy. And now, let's see one of our Subat equations again. Well, which displacement equation should we use? Really take your pick, right? Personally, I think this one is kind of the nicest one to use. It doesn't incorporate acceleration, though. So maybe we want to do that. Let's try this guy right here. Okay, we have an initial velocity and we have this acceleration. And now we know t. Let's use that guy. We haven't even really talked about that guy yet. Show it some love. All right. So S equals, let's go ahead and plug in some stuff. We got 2.4, and now we know what T is, that's 8, plus 1/2, negative 0.3 for A, and then we have 8 squared right here. Let's go ahead, let's clean that up just a bit. We're going to have to do some calculations, right? So we got 2.4 times 8 for that guy. 19.2. And then plus, well, we have 64 divided by 2 is 32. And I'll do 32 times negative 0.3. And I get negative 9.6. All right, so basically 19.2 minus 9.6. And if I do that, I end up getting a displacement of 9.6 meters. So my ball traveled only 9.6 meters, so it turns out it did not reach the hole. No, did not reach the hole. Okay. Unfortunate, that golfer is probably really upset. He got a par, he wanted a birdie. Better luck next time, pal. This is Mr. Knight, teaching about agriculture, teaching about golfing, and teaching about physics. I'll see you next time.